This is another probability of weather type scenario training, this one on isothermal warm layers that are above freezing for some depth. I'm Dan Baumgart, the Science and Operations Officer at the Weather Forecast Office in La Crosse. A quick review of the top-down approach, and what we're going to be talking about here is a little bit on the warm layer, depicted here in this sounding here, big monster warm layer here to almost 9 degrees Celsius in yellow. And just a quick reminder that when Rauber did some of his work in 2001 looking at precipitation type forecasting, the max warm layer temperature and the max warm layer depth had a fairly good correlation. It's somewhat nonlinear. You can see a little bit of a curve in here, but the linearity of it measured on the correlation coefficient 0.8, which is not too bad. So we use that stronger correlation to assume a depth to max temperature aloft ratio and use the max temperature aloft to as a proxy to the depth. So that's kind of where this warm layer assessment had its roots. So when we look at this warm layer, we're obviously seeing the warm layer max T around 9, and it's proportional to some depth. So as the warm layer max temperature cools, that depth would decrease in a somewhat linear fashion, nearly linear fashion. So the situation that we're going to talk about in this training is when we have a violation of that depth versus max temperature relationship, and we start to see this instead of this triangle here warmer than 0 Celsius, we start to see a more isothermal profile where the depth obviously here is not proportional to the maximum warm layer temperature. So the impact here is that it fails the assumption of the depth. And so if we picked off the warm layer temperature here, it might be somewhere around 3 degrees Celsius. And you see here in the max temperature aloft or wet bulb temperature aloft curves, we see that sleet in this case would be one of the main forecast types in this scenario. That's 100% probability of sleet here, mid-range probability on freezing rain. But this depth would probably entirely melt the hydrometeor of ice coming into the warm layer because of the depth, and therefore our solution would come out on the liquid side with a very shallow cold layer here, not giving us an issue of refreezing. So in this case here, we're looking at the top-down approach and probability of weather type wanting to yield a pellet forecast when in fact freezing rain would be a more likely outcome. So how does the forecaster adjust to that, and how does the top-down approach try to adjust to that? So these deep isothermal layers like this one depicted here are typically rain. The ice is melted and obviously comes into this warm layer for some depth and melts to completely rain. If the surface temperature is wet bulb temperature especially is near freezing, we have the possibility of some freezing rain in this scenario. But in the probability of weather type and forecast builder, we really have two main areas that we can assess for probability of type, and that is the max wet bulb temperature aloft and the surface temperature at the surface. So obviously these two are the points of assessment in the probability of weather type. So for isothermal layers, we really come down to three scenarios. I've included the first scenario. It's not truly an isothermal scenario, but for completeness, I wanted to keep this environment in the table to round out the training. So there's a few different things we can look at. The traditional probability of weather type training, it talks about being cold at the surface with a temperature below 32 degrees, and then we assess aloft when we have a surface temperature of 32 or less. That actually in the code for the probability of weather type kicks in the use of the max temperature wet bulb temperature aloft curves that we referenced on the last slide, and those have various outcomes. But what happens when we warm up our surface temperature? Well, then we start to try to assess in the probability of weather type the likelihood that we're going to have somewhat of an isothermal layer above 0 Celsius. So one of the keys is to look at the max wet bulb temperature aloft once our surface temperature warms above 32 degrees. So the max temperature aloft, then, we make some assumptions here between 0 and 1 Celsius when it is that warm. For example, this case here that we see on the left, that we have a isothermal layer when the temperature is around 32 to 36, that we have somewhat of an isothermal layer between those 2 points, and that the isothermal layer is close enough to freezing to yield some of the different precipitation types that might be found right next to the freezing mark. So we have an impartial melting, if you will, of those hydrometeors. So for snow and sleet, we actually use the max wet bulb temperature aloft curves. And so within that 0 to 1 Celsius range, that would yield probabilities greater than 80% for snow, and actually yield probabilities less than 15% for sleet. So actually sleet would not be included in this forecast for case 2 because it's so low. So I did include pellets here and sleet just to show you for completeness, but it really won't show up in your forecast for that 0 to 1 Celsius range. Rain is set to 100% for that for this case here, and then freezing rain is also possible. It's only possible when the temperature is 33 Fahrenheit and that wet bulb temperature is less than or equal to 32 Fahrenheit, and this is really based on the FRAM research for these types of environments when we have liquid falling to the surface with temperatures near freezing and wet bulb temperatures of 32 or less. Finally, as we continue to warm our warm layer, we start to assume that we are getting more into a rain scenario in the probability of weather type. So as we warm, as long as the surface temperature is above 32 Celsius or 32 Fahrenheit and our max temperature aloft goes above 1 C, we are in a 100% rain probability scenario, with also the probability that we could have freezing rain provided that our wet bulb temperature, again, is at that 32 degree temperature or less. So the important items to key in on for the probability of weather type in these isothermal layers is, first, surface temperature. If it's ever 32 degrees or colder, we'll use that max temperature aloft curve. But once your surface temperature starts to climb, we have different scenarios that we approximate in the probability of weather type for isothermal assumptive layers. And most of the action occurs in this 0 to 1 Celsius range, and as we get above 1, really it's an all liquid outcome, either a freezing rain or a rain scenario. So let's take a case and try to illustrate what happens in the real world here for a forecaster and how you would adjust to an incorrect outcome compared to what you're observing out there in your forecast area. So in this case here, we see rain or freezing rain observed from this forecast sounding that was in St. Louis. So our maximum wet bulb temperature is somewhere in the 2 to 3 Celsius range. And so from this, you'd typically expect sleet to be forecast from the top down and probability of weather type approach. However, this is a deep layer, very similar to what we were talking about in the previous slides. And then the temperature goes down to 32 Fahrenheit here. So the forecast builder would provide a sleet forecast in this scenario where you would typically see more of a rain or freezing rain depending on the surface temperature, with complete hydrometeor melting from the ice layer that's aloft. So why would it be sleet in the top-down approach? Recall that at 32 degrees or less, we use the temperature wet bulb max TW aloft curve here. And so we fall into this 2 to 3 Celsius regime for this sounding, which puts us well into the sleet area. We would also have a mid-range probability of freezing rain in this scenario and a very low or negligible snow probability of type in this scenario. So how does the forecaster correct for it? Well, it's fairly simple. You just go into the max wet bulb temperature aloft grid and warm the max wet bulb temperature aloft here to something closer to 3.5 to 4.5 degrees to get into the all liquid and very little sleet outcome regime here further to the right. So we're, as a forecaster, moving our wet bulb temperature warmer, max wet bulb temperature warmer, and causing more of a liquid probability outcome. So let's go through this sounding scenario in the grids here. We've got temperatures that are, let's go back to temperatures that are all below freezing. So again, we're kicking in the max wet bulb temperature aloft curves. Our dew points are cooler than that. POP is 100. QPF is not really important. Here's our max wet bulb temperature aloft, and what we're going to key in on is this area over southwest Wisconsin and northeast Iowa in the 2 to 3 Celsius range, and our prob ice and our probability of refreeze are both 100. So let's look now at the probabilities here. We're going to just stop here briefly on freezing rain and look at it. So we're in this 2 to 3 Celsius range. Again, mid-range probabilities for freezing rain. Here's our PoWT freezing rain or probability of freezing rain grid, somewhere in that 40 to 50 range, in that 2 to 3 degrees Celsius range. And as we continue moving on here, we see the probability of sleet is 100%. Okay, that's because we're square within the sleet range. And if we continue on, we see that the snow probabilities are quite low because we're at the tail end of that curve. So let's now go in and edit this curve, knowing that we're observing freezing rain in this area. And really all we have to do is warm our max wet bulb temperature aloft about a degree or two over to the 4 Celsius range. We're basically taking ice that's coming into that layer and we're completely melting it to a liquid drop. So as that ice comes in, it's melted to a liquid drop, which makes it now into the freezing rain or rain regime, depending on what our surface temperature is. And knowing what our surface temperature is, it's below freezing, we're going to have a freezing rain scenario. So let's go into the forecast builder and just rerun our grids for that highlighted time. We'll do it for today. We're going to jump right to the precipitation type grids because what I did here is I altered the max wet bulb temperature aloft, and now I'm just going to recreate the precipitation types. Kind of a quick way to move through the forecast builder. So we're going to just click on Stratiform here, hit OK with the defaults, and let it remake some of those grids that we were looking at. So let's drag that over to the bottom. And let's now just move through again some of these probability of type grids. And so here, let's just pause here on the freezing rain grid. You can see because we're now warm in that 4 degree range, we're off the right side of this curve. Our liquid curve is increasing into the above 80% range. So we're at 100% here. And if you recall, that was mid-range before we made the change. If we now go on to the sleet grid, we see that we've really taken out the sleet. We've gone into and really removed the sleet because the probabilities really drop off as you get towards 4 degrees Celsius, and we removed all the snow. So let's review what we've done here. We've taken a max wet bulb temperature aloft grid and we've really moved it over to the right here. So what we're doing is the forecaster edits the max wet bulb temperature aloft to a warmer outcome. And by doing so, we are in effect taking the hydrometeors and saying we want them completely melted. So in any scenario that you have in the wintertime, as long as your surface temperature is 32 or less, you will be using these curves. And so whenever you need a warmer type or a more liquid type to be involved, you just move that max wet bulb temperature aloft grid to warmer temperatures. One important note is that you should collaborate those changes that you make with neighboring offices for areas that are affected. So let's go into these other two scenarios a little bit more in depth here. What if this scenario stays the same that we've talked about, this sounding scenario, but we now warm the temperature at the surface? What that does is now takes us out of using the max wet bulb temperature aloft curves in the probability of weather type and puts us into this isothermal assumptive scenario here where we have to look at what the max wet bulb temperature aloft is. In this case, it is still in that 2 to 3 Celsius range. So this brings us into case 3, where our outcome will be rain or freezing rain depending on the wet bulb temperature. So for the most part, rain is the main forecast, as the temperature would now be somewhere out in this regime here, warmer than 0 Celsius or the freezing mark. And freezing rain would only be possible if the temperature would be 33 Fahrenheit, right just above freezing, and the wet bulb at 32 or less. So looking at the FRAM and how it tails off the probabilities of freezing rain once the temperature warms above 32 degrees. As long as your wet bulb temperature is equal to or less than 32, a slight amount of icing is possible for temperatures above 32 degrees. So at 32, assuming our wet bulb temperature is less than or equal to 32, our probability of freezing rain is 100. Once we warm our temperature up now to 33, we see that probability drastically tail off. And this is all from the FRAM research and is based on surface observations. So by the time you get to the temperature of 34 degrees with a wet bulb temperature of 32, your probability of freezing rain is 10%, which will not be included in any weather grids or ice accumulation calculations. All right, so let's talk about the final case here, and that is scenarios where your max wet bulb temperature is between 0 and 1 Celsius and your temperature is above 32. Remember, to enact the curves for max wet bulb temperature, your temperature has to be equal to or less than 32. So in this one, this is our isothermal near freezing situation where we have a bunch of different precipitation types that are possible. Pellets will not be included, but rain and snow and possibly freezing rain depending on your temperature. So in this sounding here, this is a typical case that we see around isothermal. And remember that these cases are very difficult to forecast. This is a forecast sounding here, but to get these temperatures correct within 1 degree is a very difficult task for any forecaster, any algorithm. These are difficult environments and subject to change through vertical motion and precipitation rate. So there's a lot that can change on these on a pretty short notice. Convective processes aloft above the warm layer can also occur to really make it difficult to forecast precipitation type in these scenarios. In this case here, our max wet bulb temperature is somewhere between 0 and 1, let's say, and our surface temperature is around 35, but our surface wet bulb temperature is 32. So we kind of have to be aware that freezing rain could be made for temperatures that are near 33 degrees from this environment across our forecast area. So let's just move through a scenario here where we try to illustrate a couple of these cases. So the first thing you're going to see is our forecast domain here, and this is western Wisconsin, northeast Iowa, and southeast Minnesota. I'm going to show you a bunch of different fields. We're going to try to capture this second case in a band that runs through. If you just key in on La Crosse County here, it's going to key in on this band right in through this area here. Now, case 2 would be where your temperature is above freezing, but your warm layer is somewhere in the 0 to 1 Celsius range. For case 3, that time when our warm layer is now exceeding, our wet bulb temperature is exceeding 1 Celsius, and our surface temperature is above freezing, we have a predominance of liquid coming down in that forecast scenario. And that's going to be, we're going to try to replicate that down just south of La Crosse. So let's just kind of move through some of these grids here. We see our temperatures here, 33 warming to 38. And then below freezing all to the north. So this is the area first that you would assume that you would expect actually to use those different curves, the max wet bulb temperature curves aloft, because our temperature is less than 32. It's this area where we're greater than 32 that we start to see some interesting results here, where our isothermal assumptions start to kick in. So we're going to take a dew point and make it just 1 degree less than the temperature grid. Pretty easy to remember then. So in La Crosse County, for example, we have temperature 33, dew point 32, which will kick in some of the freezing rain and FRAM output in this scenario. So this white line, this dashed white line, will assume the 1 Celsius temperature. I've put this dashed line in here. So everything northwest of it for this regime here is between 0 and 1 Celsius. And then to the right or southeast of this line, I've got temperatures that are greater than 1 Celsius. Remember, and that will kick in case 3, and to the north of that line will kick in case 2. Let's look at the rest of the grids. We've got a we've got a probability of ice present grid here. That's going to be 100%, and probability of refreeze is 0. So look at some of the probabilities here now. So our probabilities for rain, remember, come in when our temperature is greater than 32. So anywhere the temperatures are warmer than 32 Fahrenheit, we have a 100% rain grid. Let's continue moving on here to the freezing rain grid. Yeah, just to remind you what the temperatures look like there. Let's take the temperature and just highlight those areas that have 32 degrees or less to make it a little bit easier to see. We're just going to make a highlight edit area here. So there's our 32 degrees Fahrenheit line. And there's our rain very sharply, anything warmer than 32. And that's our freezing rain area. So let's look at, again, that is where our dew point now, according to the FRAM, is 32 Fahrenheit. And our temperature is actually 33 Fahrenheit. So temperature 33, dew point 32, that kicks in a little bit of a probability for freezing rain and ice accumulation in our scenario here. You also see a 10 here. That's where temperatures have warmed up to 34 degrees Fahrenheit, and that will not be any icing inclusion in that scenario area. And there's that 32 Fahrenheit dew point line that I had talked about. Our probability of sleet is not included in this scenario. Remember, it's less than 15%, so it won't be included in the forecast. And the snow probability there, up to 1 Celsius, uses the max wet bulb temperature aloft, which is always going to be greater than 80% in this scenario. And there's the probability of snow. So if we just look at our weather grid here in this scenario, we see that we have snow up to the north. We have some rain and snow mix with a chance of freezing rain because the wet bulb temperature is 32 degrees or less, and then rain off to the southeast. And there's our accumulation grid in that transition zone. So that's kind of a review on how the isothermal layer is used in the probability of weather type. So that concludes the probability of weather type scenario training on isothermal warm layers, and hopefully gives you some perspective on what to expect when you're in these scenarios in the grids. Remember, these are difficult forecasts to make for precipitation type forecasting, and can change fairly dramatically with small changes in the environment. Certainly convective processes will not help your forecast difficulty. So good luck.